We are recording. All right. Great. Well, welcome everybody to the April meeting of the Colorado Hydrogen Network. Got a lot of interesting things that happened this past week to talk about. You can see the agenda here. We're going to talk quite a bit about the conferences that happened this past week, and we've also got a company overview. We've got Patrick Vincent here from OMC Thermochemistry, and I'm just scanning the list here to see if Patrick is. Yeah, Patrick's there. So very good. Well, without further ado, I'm going to go ahead and get started here because we do have a lot to talk about. So there's some good expos and other things coming up, although Germany might be a bit of a stretch for a lot of us to have the budget to go do that. But there is this Hydrogen Technology Expo that's down in Houston, I believe. Yeah, that's coming up in June. And then, like I mentioned, the expo that's in Germany in October. Advanced Clean Transportation Expo would have liked to have gone to that, just didn't have the budget for doing that this year. I've been in the past. It's really a good event that's coming up quick. So if you haven't made plans, you probably aren't going to do that. But just want to point those things out. All right. So, Patrick, are you kind of queued up and ready to go? We'll jump into your presentation. If you're set, I'll stop sharing.
Yeah, I'm ready to go. Can you guys hear me okay?
Yeah, yeah, we can. We can hear you well.
All right, excellent.
All right, we got your screen.
Okay, great. So it's nice to meet everyone. I'm a lot of unfamiliar names on the screen, but my name is Patrick Vincent. I'm a senior process engineer at OMC Thermochemistry. We're a small startup company, a spin out of the University of Colorado Boulder, so CU, local here. And what CU or what OMC is trying to do is commercialize a pathway for hydrogen and syngas production that's thermochemically based. I'm going to give you guys a little bit of an overview. Before I do that, though, I'll just talk really quickly about my background. I'm a chemical engineer by background. I have a bachelor's degree from the University of Pittsburgh. I worked in Texas for ExxonMobil for about 6.5 years. I did a variety of things there. I was a design engineer, project manager, worked in polyethylene manufacturing, and then did some business analysis and techno-economic analysis. My latest role there was termed business analyst. So wide variety of things, and I use all of those things at the startup company. I'm going to skip over this slide or be pretty brief on it because I think this audience is pretty well suited to the challenges of industrial decarbonization. The point of this slide basically is that there's a lot of uses potentially for hydrogen and for synthesis gas. I think people are probably familiar, but that's a mixture of hydrogen and carbon monoxide. And there's commercial pathways for it to be uh, converted into basically drop-in fuels. So I'll touch on that very briefly, but I'm going to focus mostly on hydrogen today. We're a pretty small team. We were founded in 2021. Um, the uh, the research basically was around a metal oxide powder. Let's see if I can show it on the screen. That's kind of the core of the IP. The company has an exclusive use license to the material and any commercialization efforts around it. And I'll talk more about the material and why it's special. But it took about 20 years to get to a point where it was right for commercialization. And so after, after those 20 years, that puts you in about 2021 era. Company was founded. I joined last year. And so right now we have a Series A open for fundraising, but we're still a pretty small team, a few PhDs. Britt Bowie is our CEO. He's a former Navy pilot. He runs a pretty tight ship for us. Um, and then the rest of the crew, Kent is our CTO. He was at the University of Colorado Boulder for a good while as a postdoc. And then the rest of the team has a variety of backgrounds. I'll blaze through that. Before I talk about what OMC is doing, I'm just going to talk really quickly about existing hydrogen production technologies. I'm sure you guys are all familiar with this. Steam methane reforming, the legacy technology, provides 95% of the world's hydrogen today. Kind of a technology that's been around for 100 years or so. I consider it ripe for disruption. So I'll talk a little bit more about that. But also, I consider it to be a highly polluting technology. A couple of different reasons. You have basically the process chemistry that I have shown there where you're generating CO2. And then also you have uh, you're operating at a fairly high temperature. And so to get to that temperature, you're basically combusting hydrocarbons. And so you're working with CO2 emissions there as well. Electrolysis has gotten a lot of attention, um, basically because if you link it up with um, a source of renewable electricity, you can easily see where, given the process chemistry, you can easily see where we can get to a point where you have no CO2 emissions affiliated with it. And so it's gotten a lot of attention. There's some issues with scaling it. There's some issues with cost. It relies on precious metals that degrade over time. Um, and so we think we have an advantage relative to electrolysis, and I'll talk a little bit more about that. And then autothermal reforming is another emerging technology, another potentially lower carbon technology. It does use oxygen as part of the process chemistry, which is energy intensive and facility intensive to generate that oxygen. And then there's inherent CO2 emissions affiliated with the chemistry as well. So what OMC is trying to do, that metal oxide powder that I talked about, is an oxygen carrier. And what we're trying to do is commercialize a platform for that. And so I'll talk a little bit about the chemistry on the next slide, but the key piece is basically that we're trying to use my background's refining. When I was with ExxonMobil, we're trying to use something called a fluidized catalytic cracker, which is going to be familiar to anybody that has a refining background. We're going to try to use that same format um, to make large amounts of hydrogen. And basically, we're going to be doing that by passing this material back and forth between two reaction systems. So here's the chemistry itself. You basically have the first step. Hoping you guys can see my cursor. The first step on the left side, we expose the active material, this powder that I've been talking about, to a reducing environment where we basically pull the oxygen off of the material. And then we pass it over to a second step, a different reactor, where we then expose it to steam, and that liberates hydrogen. And then we basically just repeat that process over and over again until you're making a large, meaningful amount of hydrogen. Uh, and so it's a pretty efficient process. We've been talking to it's about 90% efficient, which is, at large scale, about 90% efficient. I will say about all the other technologies that I talked about, I'm not here to bash on electrolysis or autothermal reforming, really. I think there's going to be a lot of winners in the hydrogen space simply because there's so much demand for it. And so I think, electrolysis probably fits at small distributed scales. Autothermal reforming probably fits in large hydrogen hubs. And then what OMC is trying to do fits somewhere in the on-site generation of hydrogen, somewhere kind of in between those. So I think
Patrick,
that's important to mention.
sorry, I wanted to interrupt you and just be sort of clarified here. The raw material inputs, just like with electrical electrolysis, is the water. Is that right?
That's correct.
Okay, all right.
Um,
So you're not taking in any kind of natural gas or anything here.
no, not in this process. This is our green
Mhm.
process. Let's see. So that's actually a good lead into my next slide. There is a kind of what we consider probably our first market. We have an intermediate stepping stone where we have the ability to use methane as well. And so what's different about this is that the reduction step is provided by, or the reducing environment is provided by methane instead of nitrogen. And so what that does for us is we're basically able to make product in both the reduction and oxidation step. So for the same amount of capital, same amount of facilities, we're able to make, you know, 6 or 7 times the amount of hydrogen, which drives your cost way down. And I have some cost curves that I'll show, but we didn't really think that this was going to be a viable option for us until we started talking to some large industrial groups. Um, and they basically said, hey, we have waste heat, we have waste methane. What can you do for us? And so we started looking at this. But basically, what you do is it's something very similar to steam methane reforming on this side. It's really a partial oxidation reaction of methane into synthesis gas, syngas, then paired with the water gas shift, where you're adding additional steam, and you basically get 4 molecules of hydrogen out. Kind of every hydrogen that goes into the process comes out as usable product, and then we're able to take this CO2 and sequester it.
Hey, Patrick, just a quick question. This is Liam Noai. Your material, you said it was kind of spherical powder or whatever. Is
Yeah,
it porous? Is it like a zeolite sort of thing, or is it um, kind of more of a dense spherical particle?
yeah, it's more dense than a zeolite catalyst. It is an iron aluminum or iron aluminate spinel,
Okay.
iron rich. So it's a lot more, and I have data on this, but it's a lot more mechanically robust than like an FCC catalyst would be, like zeolite.
Yeah, so it's not also not like a sponge-like material. It's hard and
Mm-mm.
dense, like you're talking about. Okay. Yeah,
Yeah.
better for
Yep.
fluidized bed. Thanks.
Yep. Good question. So I will keep moving. I have some comparisons to the OMC process relative to some others. I have steam methane reforming or SMR. I have the electrified version of SMR or ESMR. I have autothermal reforming, and then another technology called chemical looping reforming, which is pretty similar to the OMC process. It just requires an additional step. But basically, the kicker here is that the OMC process projects to be the highest energy efficiency out of all of these, which enables a lower cost of production. And then additionally, and that's, lowest cost of production independent of any incentives. And then when we start looking at incentives and looking at the state of carbon capture and what can be achieved there, we can get to a point, our emissions are inherently lower, and we can get to a point where we can capture that full $3 a kilogram of 45V benefit. So we're excited about that, obviously. You're making hydrogen at a price that's
Question,
much lower than $3 a
question,
kilogram.
Patrick. You said oxidization. So, at what temperature the oxidization happens, and then does it require to pressurize the chamber as well? And if that is true, at what pressure and what temperature the oxidization happens? And is there any byproduct after that beside the hydrogen?
So I'll start with the byproducts. There are minimal, I would say. The selectivity in the lab is basically near perfect. So I would say no byproducts. The temperatures are similar to those that of steam methane reforming, so industrially relevant, maybe slightly higher. And then the piece about a pressure swing. So between the two reactors, we keep them the same temperature, approximately isothermal. There is a little bit of a pressure swing in between the two. We would operate the oxidation step at about 5 bar, and then the reduction step is closer to 1 to 2 bar. Nothing too crazy pressure wise.
Yeah, that is quite normal. So, can it be done at the ambient temperature?
It can't be done at ambient.
Okay.
So I have these cost curves that I promised. I don't have any numbers on here because we don't share those without an NDA. If anyone's interested, I'm happy to work down that process uh, at maybe a later time. But the kicker, the real key here is that we can generate green hydrogen at costs lower than electrolysis technologies as long as our scale is large enough. Like I said, I think electrolysis still fits in at a variety of scales, particularly on the smaller end and the more distributed end. And then the existing technology, steam methane reforming, we can beat out as well. And so we're excited about that as a potential. We can generate methane or generate hydrogen from methane at lower cost and lower emissions. So we're excited about that potential. I promised I'd talk about syngas. Going to do so very briefly. We can also, when I look at this process, instead of just exposing the active material during the oxidation step, instead of just exposing it to water or steam, we can also co-feed carbon dioxide, and that allows us to make synthesis gas. And so that has a bunch of downstream processes. I'm sure people are familiar. You can make methanol, you can make jet fuel, and so our process is higher efficiency than the existing, and so the downstream impacts, obviously, we can make those fuels and those alcohols at lower cost than some of the incumbents today. So we're excited about that as well. And there's also a potential methane use case for it, where we make synthesis gas on both sides, the reduction and oxidation reaction. Our commercialization pathway is probably going to be use hydrocarbon gases, waste hydrocarbon gases. That's our kind of the first step. Basically working with these large industrial players that are coming to us and saying, what can you do with these waste gases? And so we'd like to make low carbon, low cost hydrogen for these existing industrial players and help them decarbonize some of their facilities. That's the first step. In the long term is and has always been for us to develop the green technology. And so the markets are a little bit different, but obviously large total addressable market for us to go after. So what's next for us? Like I mentioned, we have our Series A open for fundraising right now. We're raising to do a pilot facility. After the pilot, we'll raise a Series B. Then we'll move into a commercial demonstration. And then after that, with the commercial demonstration, we should have a facility that's somewhat profitable. And going forward, any growth should be financeable through normal means. So we're expecting to just raise Series A, Series B. That's really all I had. Hope that was what you wanted, Brian. I hope I moved quickly enough. And if there's questions, I'm happy to field them now, later, any type of format.
Yeah, that's great, Patrick. Well, we'll open up to some questions, and maybe I'll warm up the audience here with starting with one. Patrick, give us some kind of a feel for the scale of this. Is it only really huge industrial, or could it even be like a small on-site kind of a thing? Give us a feeling for that.
Yeah, I think when I look at the amount of hydrogen that we need to produce to basically be competitive, it's more on the industrial scale side. And that's why I talked about electrolysis as kind of like definitely still like a relevant solution for distributed smaller scale. Like we're not going to be able to touch that, I think, at the smaller scale sizes. And so we're probably in the, anywhere from like 5,000 kilograms a day of hydrogen and up would be kind of where we're looking. That's kind of where we feel our sweet spot is, anywhere between 5,000 to 50,000, kind of depending on whether you're green or blue, whether you're green or methane-based hydrogen production technology.
Yeah, well, 5,000 kilograms a day isn't bad. I mean, that's you're not starting out at like 5,000 tons a day or something like that. So, okay, that's good to know. And I'm going to add one more thing, and that is we didn't mention that OMC is actually up in Louisville, Colorado, and so you're homegrown right here.
Yes, I'm
Yeah,
sitting in Erie, Colorado right now.
yeah. All right. So, how about some other folks with some questions or comments? Got to have at least one out there. Come on.
This is Abraham. I've got a question for you. Can you hear me okay?
Yeah, we got you.
I think you mentioned it, but I didn't really catch it. What stage of development are you in? Did you say you're in the pilot, building your first pilot, or what was it?
Yes, building the first pilot. At the lab scale, we're a technology readiness level 5 or so.
Okay, great. Thank you.
Yeah, thanks, Abe.
Yeah, hi,
This is
Patrick. This is Mohammed from BNG Cleanfield. One of the question I have is, you just said using waste gases or dirty gases. So what do you mean by that? Are you talking about the flared gases in the oil fields?
Yeah, so I'm talking about flared gases. I'm also talking about a lot of times there's hydrocarbons that are blanketed with an inert, like nitrogen. Maybe I skipped over this part a little quickly, but if you have a stream that's predominantly nitrogen and kind of a dilute amount of hydrocarbon, that's something that it's going to be expensive to filter out that hydrocarbon and get it to be usable, basically. And so what we're able to do is feed that directly into our process, and use it in that reduction step because you have that combination of both nitrogen and maybe some light hydrocarbons uh, that that instead of going to the flare, we can just use right away without any additional processing.
And you said, your experimental model is just a lab bench test model. So you haven't built really a small scale reactor, thermal reactor at this stage yet.
Not quite yet. I mean, we've basically been taking a lot of our lab scale data, getting kinetics, yields, um, you know, reaction enthalpies, things like that, and putting it into larger scale simulation software, and then developing technoeconomics off of that.
Yeah, because what it required, because bench models are really, miniatures. So before you move to the commercial scale model, I think, you have to put together a model which will be at least 1 to 2 megawatt reactor, and you should test at least for a year.
Yeah,
And anything less than that, I think the data will be not enough to go for a commercial scale.
and our pilot facility will be very similar to it's kind of, I mean, the lab scale is kind of like our CEO calls it the grandfather reactor, where, it's kind of like recognizable as a descendant. If when you look at the eventual commercial, and the pilot will be, you're basically moving out of the lab scale. There's materials like ceramics, and then obviously we're moving into steel and refractory lined vessels in the pilot. And then the commercial scale is essentially just a larger version of the pilot. We basically scale by, in a fluidized bed reactor, you scale by making the reactor wider. So the pilot will be very tall, and then we'll just basically fit more gas into the commercial scale reactor by uh, widening that reactor. But to your point, I mean, we are going to have to operate it for a pretty significant number of hours. Overall, we have a lot of different cases to test. A lot of the technology is really flexible, and so we're going to want to get all of those and get all those fleshed out as much as we can before we move into commercial demonstration.
This is Carl Rifkin. I had a quick question, and you may have addressed this, and I may have missed it. Is that the hydrogen you're producing? What quality is it? As far as the what remaining contaminants would it contain?
So the reaction, given that the conversion, so for the we can get as basically, in the 99.9 some number of nines percent, because we have a process that's incredibly high conversion and incredibly high selectivity. And you
So
basically
can
are
you
only
get
separating it from
fuel cell vehicle fuel cell quality hydrogen?
I'd have to look at what I'm actually not familiar what the um, purity requirement is.
Yeah, there's there a set of contaminants plus overall purity that you have to meet. There's an SAE standard. I don't know if you're familiar with the J2719, but you might want to look at that. I don't know who you anticipate would be your end users, but obviously if your end users are going to be fuel cell vehicles, having fuel cell grade hydrogen as an output would be, beneficial.
Yeah, it's a good comment. I think initially we're definitely more on like the industrial customer side.
Hmm.
But my general feel is, I mean, I took some notes down. I'll take a look uh, at some of the standards. My general feel is that at least in uh, the oxidation side of the process, since your only input is basically water, deionized water, demin water, I think we could probably get there. But it's a great comment.
Yeah, and there's different grades of hydrogen. There's what they call a merchant grade hydrogen, which is what most industrial hydrogen is. So, it depends on your market, but you might want to take a look at the various standard hydrogen standards and see, whether it's worth going after, for example, the vehicle fuel cell grade hydrogen, because that's the most difficult standard to meet.
Mm, I'll take a look.
All right, great questions. We got some other questions.
Yeah, good.
This is Della from Ristec Solutions. Sort of following on from the previous question, you're talking about doing large scale production. So where do you anticipate the demand is going to come from? And what would be your plans with regards to transportation? Is it demand such that you would need pipelines? Would it be, ship? Would it be truck transportation? What do you envisage there?
Yeah, that's a great question. So our vision is essentially to be, we'll always, it's always easier to be co-located with an existing facility, and that's kind of what we're thinking, is to basically um, be in a position to um, take inputs from an existing industrial site, make hydrogen, and ideally the hydrogen would get used basically on site, almost with ideally not a whole lot of holdup in between our process and the process that it's getting used in. And that way you mitigate a lot of those transportation questions, specifically for hydrogen, transportation and storage, I guess questions. Does that make sense? Did I
Yes,
explain that
yes.
well?
Thank you. No, I appreciate that. Thank you.
Yeah. Hi, this is Mohammed again. So you explained, of course, oxidation, but, of course, temperature and pressure, these are the two other parameters involved. But at the same time, the input, you said some metal ores. I did not remember. So you said some metal ores. So I'm trying to understand what is the really backbone of this whole system. Because thermal, using thermal reaction, splitting the water molecule, using using oxidation, that is quite normal. People have done it, but how you do it exactly, at what temperature, what pressure, and whether it is using one chamber or two stage chambers, and then what is, the input or what is it exactly? Exactly, is that it? That is the one which is actually the backbone of the system, the metal ores, whatever, you guys are using, which you don't want to say exactly what it is.
Yeah, I mean the backbone is definitely this let's
Yeah.
see, this metal oxide powder. I mean it's iron and aluminum. We have the ability to make it. There's multiple third parties that we've worked with to basically prove out that they can make it and that it's repeatable. Make it in small quantity, large quantity, repeatable, spherical. You know, in a if you know anything about fluidization, like a Geldart Group A powder, so readily fluidizable. For people who don't know, that basically just means that it has a certain particle size distribution. And so we expect to be able to fluidize it in 2 chambers is the goal, just because that's the that enables it to be a continuous process. So that's going to be, directionally more efficient than a batch process when we're just changing the gas compositions. There were a few other questions in there. I think I've talked some about temperatures and pressures. Temperatures, similar to steam methane reforming. So I think somewhere north of 1,000 C, and then pressures that are 5 bar to anywhere between like 5 bar and 1 bar gauge. But really the backbone of the technology and why this hasn't been done before is it all comes down to this metal oxide powder that's more resistant than the previous state-of-the-art basically carrier for this is called cerium oxide. And there's some issues with over time thermal and mechanical attrition with ceria that this powder doesn't experience. And so actually, I got a backup slide. This is a third party. We basically had them do mechanical attrition testing on our material. And so this benchmark, I think we talked about zeolite catalyst, the FCC catalyst that exists today, and basically every refinery around the world. The higher number means more attrition. And then, so this is our benchmark, and you can see that at a range of different formulations, our attrition index is much lower. And so that's kind of the really, if I were to talk about the backbone of the process and the key advancements, it's all around that active material metal oxide powder.
Another question I have is you said, the cost can be, what, $2 to $3 or $1 even you said, I think $1
Yeah,
per
it
kilogram.
depends. Yeah, it depends on the inputs.
Okay.
I could tell you that if we're, at the current purchase power agreement pricing in the futures, as I'm watching those go up, basically they're sitting at about 6 cents a kilowatt hour right now. I think we're somewhere in the, north of $3 a kilogram. If you're able to pair this with a renewable energy source that offers lower than that, then I mean it's basically the majority of the cost. It's similar to other technologies, but your electricity cost ends up being about 70% of your final unit economic cost. And so if we can pair it with something that's in the 2 to 3 to 4 cents a kilowatt hour, you start talking about $1 to $2 a kilogram. If you're at 2 cents a kilowatt hour, then we're well below $1 a kilogram for hydrogen.
Yeah, like when you compare, let's say, producing hydrogen through electrolyzers, which is the most, other than SMR, which is the most common technology people are using these days. And when you compare with all these new innovations, like yours, and many other people, they are working on different technologies. I came across many. But when you compare, compare with the cost of hydrogen per kilogram versus, any of this new innovative technology, people always claim they can bring down, from $3 to $4 versus, maybe $10 to $12 or $15 through electrolyzers. I don't understand what is the source of the power, because to run the whole system you need a power. So if the power source is same exactly whether you are using electrolyzer or this technology, the cost of the electricity is going to be same. So basically, so cost of electricity is directly proportional to the cost of hydrogen production per kilogram. So how can we bring down to $3 from $10, $12?
see if I can jump back. I'll just do this. So, I mean, the only way I can answer kind of the best comparison I have for you is like holding all other things the same. Our process projects to be able to do better than electrolysis, any of the electrolyzer technologies. So basically, I mean, once you, because this is all, I think I said 6 cents, but close enough, per kilowatt hour. These numbers all come from, a 6 cents a kilowatt hour across the board. So, if this goes up, then everybody shifts up. If this goes down, everybody shifts down. We're just confident that we can do better.
Well, Patrick, a lot of your energy is coming from heat. Are you assuming that's waste heat?
Yeah, and that's the other thing that I was going to mention. These numbers assume that we use no waste heat, but our process heat is kind of we do readily accept it. Let's look. Oh, well, all right. Well, I'll flip to this slide, but for this step, we can readily accept waste heat, and that brings our electricity usage down. So that's another reason why I think we talked about this, but another reason why I think it makes sense to co-locate an existing industrial site, depending on the quality of the waste heat that they have available.
Okay. Well, I tell you what, at this point, why don't we move on to the rest of the meeting? Patrick, this has really been interesting. Thanks. I saw in the chat, Keith Whipke said, "Hey, how about a field trip sometime?" I assume you probably don't have anything to show yet, but is that not true?
We have a lab at CU that we are more than welcome to host people, as if they want to go in and see the lab scale reaction facility we have.
Well, there's a thought. Maybe what we need is a CU field trip, and we'll look at your lab, and we'll look and see what's going on with natural hydrogen and some other things as well. But that's for another time. But Patrick, why don't you put your contact information, just your email or whatever, into the chat so folks want to reach out to you, and of course they can reach you through me. But thanks for the overview. This is interesting, and it's a little bit different than the normal way of making hydrogen that I shouldn't say normal, some of the more common ones that we've been looking at. So
thanks for having me.
Yeah, absolutely. So, all right, I'm going to go back to sharing my screen and kind of move along here. So, wanted to mention that the company Quantron is back, and I saw Buford was on. If you're still on, Buford, I don't know if you want to comment at all. I just threw up a couple of trucks that Quantron has, but I'm not sure these two are available in the U.S., and I'm not real sure what the status is of Quantron coming back out of the bankruptcy they had. Can you comment at all, Buford? I mean, are you still there? Buford was on. All right, we'll save that. We'll put a bookmark in that one. But at any rate, it's good to hear, especially after we heard about the demise of Nikola. All right, so last week was a busy week for hydrogen in Colorado. We had the Colorado School of Mines Hydrogen Symposium, which was put together kind of I don't want to say last minute, but it was kind of quick. That was Monday and Tuesday, and then there was the Geologic Hydrogen conference that happened on Wednesday, Thursday. Elliot, you got your hand up. Go ahead.
I'm sorry, I was a little late joining here, and I just heard this last part about Quantron, which is good news, hopefully. And but I can give you just a little feedback on what's going on with Nikola, if you would like that.
Sure, yeah, go
Nobody
ahead.
else has shared. From source that we've been working with them, and they have the Lucid bought the assets of the building and all of that from through the bankruptcy court, and they are not going to be building hydrogen trucks, but all of the hydrogen assets, the trucks, the equipment, all of that, all of the customers are remaining in the bid process right now, and there's two bidders. and those two bidders are coming up with a capital to close out. Hopefully, it says that the court has given them until Friday to get that accomplished, but my party has said hopefully they think by tomorrow they should have an answer, and the basic part of that is about developing the fueling network, which puts us near and dear to them, and number two, about actually coming up with the money to build their facility. They need another facility, but it's not to build the trucks that we're already seeing. It's to build the new Generation 2 trucks that they've designed and they're coming out with. And the plan is to to lease back the existing facility from Lucid until such time as they can move into a new facility. So Lucid would obviously have to engineer, design, and build new equipment to manufacture their vehicles. It's my understanding that it may or may not be mid-sized trucks, but electric trucks. But it's I think it's a favorable deal for the uh, um, the ongoing people that are with Nikola. Lucid is going to keep 300 people on board employed from the bankruptcy, which is good from that perspective, and that's all public information. Let's see, what else am I missing? I think, you know, um, it's a reboot for both companies. A lot of money spent early stage in development of an incredible. Both of them have really nice equipment. Okay, the problem is building that infrastructure, and the lack of the rest of the infrastructure, of which we're trying to focus on, and of course, our friends over at New Day as well. We need that across the country. We need that in the markets where they're going and as they develop. And unfortunately, we lost traction with the loss of funds so far from the federal government. But the states have picked up the mantle and are moving forward as best they can. For us, we're working in Michigan, Colorado, and hopefully in Texas here soon. But that needs to happen across the country. And last thing I'll say is that if you guys follow the news, China's built a cross China highway that's all hydrogen, which is impressive. And what they're doing is very impressive. They're moving forward with the business stuff instead of this, they're doing business. So,
Yeah.
which is good, and that's encouraging from them. So hopefully, our government will get the picture and make a change, and we'll go forward from there. But thank you for letting me share that, because I'm really very supportive of both companies, and particularly all the effort and the people that we've got come to know at Nikola, as you have some of them as well. We want to see them be successful. Thank you.
Okay. All right. All right. Great. Thanks, Elliot, for that little background there. So, all right. Well, we'll switch back to talking about what's going on at the School of Mines. And around hydrogen, there's a lot. And it was really an interesting symposium to kind of hear what they're doing and what's going on. So the work kind of falls into maybe three categories here: the geologic hydrogen, hydrogen production and storage, which you would imagine, as well as a lot of work around materials. So um, Mines is very tied in with the USGS. They always have been. I know Jeff Ellis, who's very active in geologic hydrogen, is actually a professor out at Mines. Um, they are trying to help with the identifying and characterizing of where the prospecting is going to be successful for natural hydrogen, and also the techniques just to map and assess those kind of things. They're working with electrolyzers, including solid oxide, and that would, of course, include electroceramics and things around that, composite membranes and those kind of things, and hydrogen storage and subsurface systems. And as far as materials go, they're trying to find cheaper things as well as just things that technically meet the bill, and composite membranes. So there's really a lot going on there, and I have it in the back of my mind that maybe try to set up some kind of a CHN field trip out to mine so we can take a look at that. I did that once back just before COVID, and it was like drinking from the fire hose. There's a lot going on there. So the 2 day session had really four parts to it: the geologic hydrogen, the storage, transport, utilization, and then the last day was kind of a short day, and that was electrolyzers and fuel cells. Um, Quite a bit of discussion around internal combustion engines burning hydrogen, and I'm going to talk to that a little bit and as to why that makes sense. Steel embrittlement, it's not as bad as you think. There's definitely a lot of work being done there and a lot of opportunities. Also, a little bit of emphasis placed on these. I've got LOHC, liquid organic hydrogen compounds, but there's also others that maybe you wouldn't consider to be organic. And then, of course, ammonia is a good carrier, and there we'll talk to that just a little bit. Talked about using blends of ammonia and hydrogen for internal combustion turbines, those kind of things, and I'm going to talk to that a little bit more, as well as catalytic ammonia reformer or cracker, sometimes that's called. Our friends out at Starfire are busy with that, but there's work going on at mines as well. So the folks that were there, I don't know the total number of people. I mean, we filled a pretty good sized room, but we had a professor from Cal Berkeley that was there, but otherwise it was generally the School of Mines folks. We had a bunch of reps from NREL. Brian Pivovar was there. Sandia Labs and Idaho National Labs featured prominently. NIST, the National Institute of Standards and Technology, formerly the Bureau of Standards. DOE was there. Asterisk on the ARPA-E, the one person we had said he was there on vacation. He was unofficial. I guess he didn't want the Department of Government evisceration coming after him, but I say that tongue in cheek. And of course, USGS, obviously, you'd expect. A number of folks from industry, Chevron, Halliburton, Everaz Steel. I guess you can read this faster than I can say it. And then nonprofit side, Anya Richmond was there from the Colorado Energy Innovation Collaboratory. And then, of course, I was there. So, all right. I took a couple of snapshots of some of the slides as they were flying by. And this one just to show the work that's going on with the reformer, basically the cracker of ammonia. And we've talked to this a number of times before on this meeting, but these ammonia blends can really be tuned to imitate methane or natural gas, diesel, jet fuel, JP4, other things as well. Now, of course, one of the issues with using ammonia as a hydrogen carrier is that it takes energy to take the hydrogen and the nitrogen and make ammonia, and then there's some conversion loss to convert it back. So trade study obviously has to be done to see how that compares to transport costs and storage costs, if that saves you or not, or if liquefaction is maybe a better route. Here's a really interesting slide. I had known for some time that fuel cells are really the most efficient, and you can see that in these curves at the low end, either the green dotted curve on the far right there or the red line. Let's see if you can see my cursor here. But when you start getting up to the higher power output, meaning how much power are you continuing to apply with your motor that's running your vehicle, they really kind of meet. And the reason I added this second graph, which I just pulled off the internet here with the dotted line, is if you look at the slide, and this came from Sandia, they say maybe there's a gap, and you can barely read it here, but it says crossover question mark. And so this is one of the reasons why internal combustion hydrogen engines may make sense for the heavy duty vehicles. And they've got a table here that kind of talks to some of that. I won't go into a lot of detail here, but I don't think we should all just dismiss the idea that internal combustion is necessarily bad. Now, it does have some knocks because you're burning air, which has got nitrogen in it. That can be helped a couple of ways. One is by using really very finely tuned fuel air mixtures. And we have a company here in Colorado, Super Turbo, that does that. They've got a turbo that can be just tweaked for every RPM and every load. And then, uh, oh, Gerwin raised his hand. Go ahead, Howard.
Um, I'm glad to see that people are still talking about this. It's gone through a lot of, but the hydrogen IC engines are something I've been working on over the last couple of years, with one of my clients. They built some demonstration engines. They built a demonstration engine, and basically they can match the diesel engine for line for performance and brake thermal efficiency. So what really is important to think about with a hydrogen IC engine is that in 2 years, from a year and a half for 2 years from dropping the flag, you can have as many of these as you want. If I tell you 2 years from now, and I don't know how many hydrogen fuel cells I'm going to need, but I'm pretty sure I can't have as many as I want in 2 years. But I can have as many. There millions of diesel engines are made per year globally, and they're easy to the number of things you have to change. You've got to do some engineering, but it's not rocket science. It's not materials expertise, with the exception of one component which is being worked on. It is really it's a manufacturing and product development lift, not a research and development lift. And so it's like if somebody wanted, if there was a market, if there was hydrogen to burn, IC engines could be there to burn it. And it's like the easiest step. And all the engine manufacturers have basically demonstrated something. And the key component manufacturers are working on the fuel injection systems, which, because hydrogen doesn't have any lubricity, hydrogen injectors there's some metallurgy required, but that's thought to be maybe 1 year out before they're done with that work. So there's a lot happening. It's not sexy like fuel cells, but it has a lot of interesting potential. There is one of the equipment manufacturers, JCB, out of the UK, have built actually a fleet of 50 hydrogen-powered backhoe loaders. And I think they're running around the UK somewhere.
All right, good. Thanks, Howard. Appreciate that.
Yep.
Elliot's got his hand up again. Go ahead, Elliot.
I'm sorry. I've been studying a lot on and working with Cummins. Already has an engine. They've sold 500 of them to Warner Trucking, 500 ICE engines and 500 fuel cell engines, and they're in the testing phase there. And if you guys have been online or anything, Cummins has been advertising very strongly. Big, strong advertising program on hydrogen engines for the trucking industry. And they have developed their NOx is way very it's very comparable to to the fuel cells. Very close right now. So, and they're continuing to develop too. So that's great news from Howard. So a lot of good things happening in that regard.
All right, thanks, Elliot.
Plus, one last thing. The cost factors are night and day different than an ICE engine, and that's what makes it presentable and capable to hit the market. And again, what Howard mentioned, if there's fueling available, and that comes back to infrastructure. So, we're excited, but we're concerned.
Yeah, and I note that on this table, the third from the bottom, upfront cost, ICE low and fuel cell high. I don't know. I mean, I know a fuel cell engine is going to have batteries along with it, so that's going to boost some of the cost. But I really kind of question that at scale. How is it low and high, or are they pretty close?
Yeah. Well, Brian, there's a couple of things that since we're on the topic, I'll get on my soapbox for just a moment. Diesel engine components are made in the millions already with mature tooling, and there are manufacturers who are wondering what their future looks like, who are trying to figure out how long to keep these facilities running to make these very specialized bits and pieces. And all of those factories already exist and are optimized at a level that fuel cell production won't be for 5 to 10 years, I think. I think that's the key. The other piece of it is, and you just mentioned batteries, and that's the other piece of it is, there are a lot of OEMs out there that make on-highway or make off-highway equipment, especially that are small. And they could, re-engineering a machine to take a hydrogen engine is a lot less engineering intensive than re-engineering a machine to take a fuel cell electrified powertrain. So for many people, the I don't know if this will happen because of hydrogen costs, because of the political environment and all those things. But the hypothesis that we had when I was doing this work was that there was a set of people out there who would need to make a transition to low carbon, but would maybe not be in a position to make the transition to a fully electrified powertrain. And that this was a stepping stone for them because the rest of the machine is unchanged with the exception of figuring out a place to mount a hydrogen tank.
Well, that's right. And, a lot of these, especially the off-road things, have power off takes for hydraulics and other things. And so now you're going to have to electrify that, whereas it was previously driven by the engine. So,
Yep.
well, I tell you what, Howard,
I'll leave it at that.
yeah, we're starting to fall pretty far behind here. So I want to go ahead and press. I mean, this is such great stuff, though. And it's our favorite subjects. We could go on forever. I'm not even going to go into this slide. Let me do point out, though, that I just learned that School of Mines has this Global Energy Future Initiative. And the point of contact on that is Dr. John Bradford. Spent quite a bit of time with him at this seminar that we had. But I encourage you all to maybe go to the Global Energy Future website here, take a look at that, just become familiar. I would like to try to connect CHN with this because of this idea that I've got for the Clean Energy Hub, which I've shown many times at this meeting. But I really think that what the world needs is a major plan of what are all the inputs, what are all the outputs, and what's everything happening in between, so that we all have kind of an agreed on map of what things are, so we can start working on building pieces of these. And although, I'm primarily interested in of course, hydrogen and especially transportation, when you start looking at, okay, where is hydrogen from transportation going to come from? Well, one of the cheapest sources might be hydrogen wells, but transportation can't bear the cost of developing those. So maybe if you've got somebody like a data center, they could get that developed and so forth. So that's why I think it's important to have the complete picture here so that we can say, here's where the miracle has to occur before things can happen. So I want to take this to mind, see if this is something they're thinking about, see if either I can work with them or we work together or something like that. So that was the point in mentioning this Global Energy Future Initiative. I need to learn more about this, and maybe we can even get somebody on the meeting here in one of the following months to talk about that. All right, so I was very honored to deliver at least one of the keynote speeches. The other was Brian Pivovar, and then we were on a panel just talking about fuel cells and other things. And it's kind of humorously we had three Brians on the panel. It started getting a little bit confusing, but just wanted to brag a little bit that I got involved in this, and thanks to Rob Braun for inviting me to do that. All right, so I'm going kind of fast here, but I want to cover quite a bit of ground here on this. It's RMAG, the Rocky Mountain Association of Geologists Helium and Hydrogen Conference. They've held this before. It was really well attended. There was about 180 companies registered, about 250 people. Really a lot to talk about, and we had a booth. So here's the booth, and I want to give a special thanks to Mike Grimwade and Brendan Donor, left to right here, who helped me out, just kind of staffing the booth, talking to people, made a lot of good contacts there. And Mike and Brendan, I don't want to put you on the spot, but I don't know if you've got any comments about. I know both of you spent 2 full days there. Do you want to say anything?
Yeah, I guess I'd say I thought it was very informative. I mean, I'm not a geologist by nature, but yeah, it was just very interesting to hear kind of the excitement and buzz around geologic hydrogen and kind of early stages of the exploration and prospecting process for that. at this point. So I think that there's a lot of hope and promise associated with the geologic hydrogen piece, and looking forward to see where the industry goes over the next year or two.
Yeah. Thanks, Mike. Brendan, any comments?
Hey, Brian. Sorry, you may hear some kids in the background here. Uh, but yeah, I thought it was a fantastic conference. I think there is a lot of potential. I mean, the big takeaway I had was that we're still pretty early on in
Mhm.
the exploration side of things. But, something that was, I think, really promising is that it takes millions of years for the subsurface processes to produce petroleum, but there is rock that you can produce that will produce hydrogen in a matter of days. So I think that long term is pretty exciting.
Yeah, and this area is moving really fast, and part of it is because we're building on all of the work that's been done in geology and drilling and other things for the petroleum industry. And so I think that gives us a real leg up, just like having battery EVs helps us develop hydrogen EVs that much faster because some of the pieces are already there. Kind of the same situation with the geologic hydrogen. Yeah, well, again, thanks to you both. I mean, you both spent full days there, and that was a lot of help. And um, I think you learned a lot. I know I learned a lot. So let's delve into geologic hydrogen just a little bit. And I think everybody on this call probably recognizes that it's actually a source of energy. It's not just a carrier. But the other advantage that I really think is important to emphasize is that it's molecular. And molecules have advantages over electrons because they're more easily stored and for longer periods of time. Um, I think one of the most important ones is that you can transfer energy faster than you can with the electrons, especially to vehicles, things like that. Higher energy density, lower weight than batteries, even taking the tanks into account. And of course, you can use these hydrogen molecules to make other compounds, which is something that's been going on for a long time in our world. It's likely the lowest cost. I think I've got a slide I'm going to show you some other thoughts on costs, but I'm a believer that it's going to be less than 30 cents a kilogram at the well. And there's huge quantities, and we'll talk to that. So here is and this actually came from the School of Mines. So I'm jumping back and forth a little bit here. I'm talking about the geology seminar, but this is at School of Mines. And I apologize, I don't recall who put this up, and I think TEA is some kind of economic analysis, but a little hard to see. But the ranges are from maybe 44 cents a kilogram at the well up to maybe as high as $1.45. And I think these may even be high. We'll see, just my opinion right at present time. But it's those kind of numbers that we're going to need in order for hydrogen to compete with natural gas, as well as for the big truck diesel. Because as we were showing on the slides about the efficiency, a diesel engine burning, or I should say, an internal combustion engine burning diesel or burning hydrogen are probably going to use about the same quantity. And so that means we're going to have to get hydrogen down to the price of diesel, which is down toward $3 a gallon or $3 a kilogram. And so by the time you transport it or move it, you're going to need prices like this at the well. And so there's hope to do that. All right, so this was presented talking about just how much hydrogen is out there, and Jeff Ellis with USGS has done some analysis, and obviously a lot of hydrogen is going to be occurring under the ocean. It's not accessible. It might be under mountaintops, not accessible. Others may be just too dilute or too small, so you can't get to all of it, but I think the numbers he was throwing around was it's like 1.78%. So I said just under 2% actually would supply the projected energy needs for about 200 years. And this amount of hydrogen is actually more than all the proven natural gas reserves on Earth. So this isn't trivial. And if it's very low cost, that's why a lot of people are getting excited and a lot of people are throwing a lot of money at this. So It's also to some extent renewable. Now, obviously some of these pockets of hydrogen we find may have developed very slowly over a long period of time, and so the rate we want to withdraw them may exceed how fast it's being replenished. But a lot of these are being replenished. I'm going to talk to the mechanisms here in a minute, and so I think maybe some folks hesitate saying this is a totally renewable, sustainable kind of a resource, but in some ways it is. So, what are the processes that create this? Well, there's this serpentinization reaction, which is basically water reacting with iron-containing materials or minerals, which releases ferrous iron, and then oxygen reacts with that, which releases ferric iron and hydrogen. Another type is radiolysis, which is radioactive decay, which produces ionizing radiation, which reacts with the water. And then there's just simply hydrogen outgassing from the mantle. So all of this is going to diffuse upward. And so we really need formations, caps or whatever, which can trap some of this hydrogen. And that's really one of the tricks to trying to prospect for this and to develop it. So some of the things that can cause losses of this hydrogen is well, first of all, it can be stimulated. We can inject water or steam to feed the serpentinization. It can also do fracturing. Stop short of calling it fracking. That's kind of a bad word, but that would help increase the permeability and the reactive rock surface. And some of the losses are, some of it just percolates through the ground and escapes to the atmosphere. As a matter of fact, Vyacheslav Zagonek, who's written a paper on this, claims that the Earth is really leaving a trail just like a comet of hydrogen, which I think we've talked to this before in this meeting, but I think we have to point that out to people who say, oh, hydrogen leaks are a greenhouse gas. Well, tell you what, they're many, many orders of magnitude less than just the natural hydrogen that's coming out of the Earth. Some of it's consumed by microbes. They use that for energy. I know ocean vents sometimes they find these microbes and things in deep ocean vents, and they wonder how they could survive while they're getting their energy out of the hydrogen. Of course, some of the hydrogen is going to combine with oxygen to form water or CO2 or carbon monoxide to form methane. So here is a composite map, and one of the things they did at the seminar was to kind of go into all of the bits and pieces that make up this map. But here's kind of a best guess right now. The darker blue is, as they call it, the prospectivity of where we think there's hydrogen. And then the red dots are actual observed hydrogen. And these are not hydrogen wells. A lot of these could have been petroleum wells or other things, but they observed the hydrogen. And there's a pretty good correlation. They're trying to understand some of these things, like down here in Texas, you've got very, very low prospectivity, but you've got some sources. And so that needs to be understood, and they're certainly working on that. So, I mentioned Vyacheslav Zagonek a minute ago. This is actually data that was taken from his paper, but he was at the show, and it surprised me a little bit because I hadn't heard he was going to be there. For those of you who don't recall, Vyacheslav had a company, Natural Hydrogen Energy, that drilled the first well in North America that was in Nebraska. It's capped now; it's not being used. But he wrote a seminal paper on this and is a pretty prominent figure in the natural hydrogen area. But he needed a paycheck. Natural hydrogen wasn't quite getting him there. So he now has a company that is doing data acquisition and analytics for geologic hydrogen, and kind of acting as a reference solution for the folks exploring and monitoring. So it was good to see him. It was a nice surprise when he walked up to the booth, and good to see him. And I did do a podcast with Vyacheslav back in 2022. If you happen to not have heard that, you might tune that in. And also, his paper is on the CHN website. So if you want to go and look at that, it just basically is a survey of where hydrogen's been found throughout the world and why there's been so much and why we didn't really know about it until just recently. So here is a nice map, I guess I'll say, of where the hydrogen exploration was going on in 2024. And it's a little bit hard to see, but I mentioned that Vyasheslav's well has been taken over. I think Hytera owns it, but you'll notice in Kansas, and there was a news release about the exploration that's happening in Kansas. That's Hytera as well. And I think they show up. I thought they showed up another place, but that's it. But you can see there's an awful lot of interest in things going on here. Masood, go ahead.
Thank you. Very useful information, Brian. This hydrogen, geological hydrogen, is this formed or extracted in pure form, or the one like it stays in the earth in with the hydrocarbons, and there is a reaction, and you pull out the hydrogen from the hydrocarbons?
Yeah, that's a great question. So it typically is not absolutely pure, but one of the benefits to finding it is that it usually occurs with helium, and helium is a really valuable industrial gas as well. And so I'm going to actually talk to that in a second. You're kind of anticipating a lead into my next slide. So well, let's see. I think it's here. Yeah. So wells produce both hydrogen and helium. There's some other contaminant gases. There may be a little sulfur. It's my understanding that the hydrogen doesn't really occur that often with methane, although there may be a little bit. So, yes, some purification is going to be needed. And that can be a little bit tricky because one of the ways you might try to separate gases is with cryogenic distillation. You take it down to the boiling point or just below of a certain gas. You can bring one gas out as a liquid. But when you're finding hydrogen and helium together, and you want to conserve both, you don't want to really throw one away, that gets a little bit tricky. Now, today, what they do to recover helium is they'll use pressure swing absorption. And that could recover hydrogen or it could recover helium, but not both, because typically, in order to get the helium out with this technique, you would combine the hydrogen with oxygen and just make water out of it. And now you've basically thrown it away. And that's his point here. One gas is sacrificed to recover the other. So we need some other techniques. Now, I've done, let's see, 2 podcasts now with a company called Hyatt. They are in the Netherlands. And they have an electrochemical compressor and an electrochemical purifier. And basically, those look like a fuel cell or an electrolyzer. They're a stack of membranes with some metallization and so forth. I believe that can be used for, you would use that device to separate out pure hydrogen, and then whatever's left over is going to have the helium and maybe the other contaminants, and maybe at that point you could extract that. So I put a call in or an email just yesterday to my contact in the Netherlands at Hyatt to ask them about that, as well as to talk about the scale here. You know, is their technique just too costly to try to separate those two? But this wasn't really highlighted as a big concern about trying to separate these out, but it may be. So so stay tuned, and maybe there'll be some podcasts or some other discussion about that. So did I answer your question, Masood?
Yes, thank you.
Okay, yeah, you're welcome. Another thing that came up was this idea of regulations and best practices and permits and fees and everything in other states for geologic gas extraction for the hydrogen and helium. And the example that came up, that we had some folks here that were there from Minnesota, where they discovered up in the peninsula up near Lake Superior helium. And so they wanted to put some wells in. And Minnesota has never had any gas wells or anything like that. And so, of course, initially the state authorities were, oh, wait a minute, you know, how do we permit this, or how do we approve it, or what's important, and so forth. And so that team was very complimentary of people in Colorado. I don't know if it was who it was exactly, but they came to Colorado to find out really how we have done regulations and fees and things like that. Fees are a big issue because if you look at oil and gas, obviously deep pockets, very well established. For them to pay $25,000 for a permit is nothing. Whereas if you've got a startup company that's trying to develop a hydrogen well, those fees could be, pretty onerous. So that's kind of an issue. I don't know that we've got it completely solved here. I know we do for oil and gas, but maybe not for hydrogen or helium. So stay tuned on that. We'll see where that goes. But that's just something else to be kind of aware of. All right, so that is all I really had to say about the two webinars, or I should say seminars, symposiums. I know Mike and Brendan, you already talked, but if you've got anything to add to what I've said here, or if anybody has any questions or comments.
I guess one thing I thought was interesting, and I think it was really highlighted in the final keynote address after Brian and Brendan took off, but the lady was kind of summarizing just conclusions of where the geologic hydrogen industry and findings are to date. And it kind of sounded like there wasn't a whole lot of thought that we would just find a capped pocket of like pure hydrogen just sitting there underground. It sounded like where there's potential more promise is with, I think they called them like chimneys, places where there's hydrogen percolating up from like the deep mantle or core, and can be found in flows that are high enough that can be extracted. So I thought that was interesting that maybe the recovery methods would be fairly significantly different from, say, like a traditional natural gas pocket or something like that. And that's kind of why there hasn't been established hydrogen well to date, whereas maybe there have been for helium or for some other gases. So I thought that was
Yeah.
interesting, and that kind of changed my perspective a little bit on how we go about accessing the hydrogen that's down there. So.
Yeah, thanks, Mike. And of course, the other issue is that you could find a lot of hydrogen, but you got to have somebody to sell it to. And possibly one of the first real strong uses is going to be in Kansas, Nebraska. That's farm country. You can get some hydrogen, turn it into green ammonia. And so that may be the the entry point, maybe I'll say, for trying to develop some of these resources. But yeah, there's a long way to go. But I really got the feeling from everybody that this is moving really fast, that it's probably going to take off just because of the um, financial aspects of it and so forth. Masood, you got your hand up again. Go ahead. Hope you're on mute.
Sorry, I wanted to ask, was there a conversation about hydrogen for power generation? We used to hear a lot. I used to hear a lot I worked for power company, so that's a lot couple of years ago, but now the interest is sort of dying for power generation. Was there conversation on this topic? And is that your impression also for power generation is probably not as suitable as it was a couple of years ago or thought to be?
Well, that discussion didn't come up too much that I recall, and Mike and Brendan jump in if you remember that. But I think power generation is a good use for it, and I don't think really the need or the possibility of that has decreased. As a matter of fact, I think power generation would represent a big off-taker for that resource. And so if you put a lot of money into developing the capital equipment to develop the resource, you need a big off-taker. And that could be a power plant, that could be a data center. And I think this really could be the way that data centers could get around having to force utilities to build new power plants and forcing new transmission lines to come in. Find a hydrogen well somewhere, put your data center right there, do it all on the same campus. And so that's that's a message I'm going to keep trying to get out there. I don't know if I'll influence anybody, but I do think power generation could be a very strong contender, especially early days.
Hmm.
Yeah, I
Well,
would agree, and I don't know that this conference necessarily got a whole lot into applications
Right.
necessarily. It was mostly on the source and extraction and a little bit of filtering it and cleaning it up and stuff. But for me personally, that's where I see the biggest use or my biggest interest for the use of hydrogen is large scale power generation and combustion turbines and stuff. So I know a lot of people on here interested in the transportation side of uses of it, which I think is a valid use as well. But for me personally, I'm interested in applying it in large scale power generation. So I don't think that that's been canceled out at this point for sure.
Yeah, I
well,
agree. And by the way, for everybody on the call, Mike is with Black and Veatch and has had conversations with some of the data center folks and looking at their needs and so forth. So um, stay tuned. It's all changing.
well, power generation, I mean, if we need hydrogen to firm up renewables, and so you the cost of storage is so high that the economics don't work. Mike, is that not the kind of the one of the impediments, the storage cost?
Well, if you get away from wind and solar and start looking at geothermal and natural hydrogen or hydrogen from petroleum reservoirs, you don't need storage because
Hmm.
you just use it as it comes out of the ground, so to speak. Um, I frankly think that someday we'll look back at wind and solar and say, well, yeah, we kind of started there. That was a low-hanging fruit. But really, geothermal energy and natural hydrogen and some of those things, because they're 24 hours a day, right?
Right.
Get you out of those needs to store. Now, um, that being said, I also have to say that I think that in the future, we're going to have much more distributed sources of energy. If you're in the Great Plains or along the coast, there'll be a lot of wind because the wind may blow most of the time. And maybe down in Arizona and so forth, you're going to have a lot of solar. And I think solar is applicable for small applications, for homes, for rooftop, for businesses and those kind of things. But um, I think I think we can get away from this idea that we've got to store energy and just go to sources that are continuous.
Yeah, and
I kind of, yeah, go
if I
ahead.
can add to that, I mean the when you talk about storage with hydrogen currently, like Brian's saying, I mean because it's produced with electrolyzers and it truly is a hydrogen energy storage device, right? And so you've got these giant salt caverns underneath like the Delta Utah site for storing that quote unquote energy until you need to use it. I mean, I see in a mature market hydrogen being similar to like a natural gas and that it's stored in a large infrastructure of pipelines and that maybe the technology there needs some development so that it's not embrittling the pipelines and we're not losing a whole lot from hydrogen escaping through the pipes and stuff. But I mean, to me, it'd be the same conversation as we have right now with well, where are we storing natural gas that's used in power plants? Well, it's in the pipelines, right? So
Yeah, good
that's
point.
what I see.
Good point. Yeah.
Yeah.
Masood, does that answer your question?
Yeah, it does. And I think you've said something which is really important that we might be looking back at, wind and solar as being kind of the starting point because of the very low energy intensity. You need large amounts of areas to you get small amount of energy. So if we can drill a hole and get whatever hydrogen we need, it's the area covered. Energy density will be really high. That's the biggest problem with wind and solar.
Oh, yeah. Yeah, absolutely. But, they were an easy way to start and so forth. And,
Right.
and like I say, I think solar will always have applications for small distributed things for homes, maybe some buildings, those kind of things.
Hmm.
Utility scale, not so sure. We'll have to see. The market will decide, right?
Right, right. Yes.
Yeah.
Thank you.
Yeah, yeah, absolutely. Um, All right. Well, I've got just a couple more slides, but they're away from this topic. Nothing really urgent. Do we have any other questions or comments about geologic hydrogen or School of Mines or any of those things that have been going on? Are we good? Well, I showed this last time. I did want to highlight this report that CRAD, or SEP as they more commonly go by. If any of you are interested, I don't recall the cost of this, but SEP is offering CHN members a 15% discount, as well as they will donate 15% back to CHN. So if you're interested in this, I would encourage you to go to the executive summary, which I've got a shortcut link here, this tinyurl.com. That'll give you a chance to take a look and see how interested you are, see if that's something you want to purchase. CRAD really does a lot of great work around hydrogen. It's probably one of their key areas that they focus on. So a lot of great data if that can be of use to you. And then pretty much lastly, I just wanted to just keep it in front of everybody's mind that if you feel like trying to support us a little bit, individual memberships, $50 a year, startups, $200 a year, Scouts Honor, if you want to just join as an individual at 50, this will kind of help us keep our coffers filled up. Right now, we don't have enough money to do another hydrogen day. I'd have to find a sponsor or maybe rely on some of these donations. So if you're interested, if you go to the Colorado Hydrogen Network website and hover your mouse on the members, then this red join page will show up. And when you click on that and go to this page, there's a big blue button here for join as an individual or to join as a corporate. And the corporate membership includes a membership in not only CHN, but CCI. Well, it was formerly called CCIA. Now it's just Colorado Clean Tech. I've got to get our donation button working here in case anybody wins the lottery and wants to give us a big pile of money. So that's pretty much it. The podcast, I haven't done a new episode since last month, but I've got a couple in work. So you can watch for those. I've found it difficult to keep up the cadence of every other week. So these are a little bit more erratic, but still trying to get some good information out there. All right, got 2 minutes left. Any other comments, questions, anything else from anybody?
Hey, Brian,
Yeah.
it's Buford.
Yeah.
Just wanted to let everyone know we will have a hydrogen vehicle at the Colorado Auto Show this coming weekend. Electric Green was good enough to loan us one of their vehicles, so I'll be down there showing it off just so everybody knows hydrogen is an option when it comes to transportation.
Great. And Buford, as long as you're back, I had called on you before and I think you might have stepped away, but I had mentioned in one of the slides earlier that Quantron was coming back to life. Do you have anything to say about that or any comments?
Yeah, I mean, I don't have a whole lot of insight in regards to that. I know Andres Haller, who's the guy that basically created Quantron. He basically bought it. I don't know if it was out of bankruptcy or what, and he's trying to restart it. So not exactly sure what that's going to look like. Positive news, obviously, that somebody's up and running on that front, but really don't have any insight as far as to exactly what it's going to look like once they are back in operations.
Okay. All right. Thanks. All right. So Elliot, you got your hand up again. Can you do it quick?
Oh yeah, I'm fine. Hey, I put in my information in the chat there for Mike to get a hold of me at Black and Beach. But Brian, this is awesome. These are really good updates. So I'm sorry I missed earlier. I had another meeting I had to jump off from to get on here. But you notice I'm wearing a
Yeah, love
familiar
your
hat
hat.
to you. Yeah. Thank you
You
very much for all you do.
Yeah, you won that at the Hydrogen Day, I think, didn't
I
you?
did. Yeah, I won something finally.
Well, good for you. I
Yeah.
also want to comment. We got 21 people still on the call, but we were up to at least 35 I saw go by. And I was just going to say, I'm so pleased that everybody's supporting this meeting and coming out to it because I know sometimes, you get busy. But I was on an international call recently and they only had 30 people. So, I think we're doing pretty darn good here.
It's an exceptional show you put on.
Well, I put a lot into it. So thank you. I appreciate that. So,
It's a labor of love,
yeah.
and we
Well,
appreciate it too.
I tell you what, I'm a stickler for starting on time and ending on time. So I'm going to adjourn the meeting and thank you all for participating and for your support. And let's go out there and make hydrogen a reality.
Thank you, Brian. Take care.
Thanks,
Talk
Brian.
to you later, Buford. Bye.
Yep.
Thank you, Brian. Thank
Yes.
you, Bhupen.
Thanks, everybody.
See you, Brian. I
Oh,
appreciate you. All
oh,
right.
absolutely, Elliot. And keep up your hard work too. I'm support
I'll
you
tell you
however I
what,
can.
it's challenging at times, but it's well worth it. There's good traction here, things that happen, and as I mentioned earlier, I can't go into all the details, but hopefully we'll know by the end of this week about the Nikola situation. And there's a company you got to give a lot of credit for the people that hung in there to keep it going through in spite of all this stuff, and I really believe in them and what they're trying to do. So. Um,
Yeah, our
Winners
hearts
never
are with
quit and
them.
quitters never win,
Yeah,
and
yeah,
and
exactly.
that's true.
And oh, who was it said that? I think it was Edison said that so many people give up just right before they're about to make it. And so
Right?
I
There's
guess
a
never give
poem to
up as
that
long.
effect too. There's a great poem to that effect about quitting. Don't quit. It's
Yep.
called Don't
Yeah.
Quit. So, all right. Well, listen, I'm going to let you go. If there's a chance at some point in the next week, I'd like to visit with you as well.
Sure.
So I'll reach out to you.
Okay.
Okay.
Yeah. Yeah. Do
And
that and
thank
we'll
you.
we'll set something up. All right.
Thank you,
Thanks,
brother.
Elliot.
All right.
Bye-bye.
Bye.